Right. So it gives me great pleasure to introduce a newcomer to Chain, and I'm to blame for that. Sorry, Sarah. So Sarah is also my colleague of a few months in Tensor. I work for Tensor International Limited. I'm in the design department. Sarah has joined us about 2 months ago in the manufacturer plant. So Sarah Mugabo is a process and product engineer of strong academic background. She possesses a Bachelor of Engineering with honors in chemical engineering from University of Manchester. She also has a Master's of Science in Chemical Engineering from Swansea University, but she also has a PhD from in Materials and Science and Engineering, Materials Science and Engineering from Swansea University too, and her thesis was on the process and materials effect in organic coating of architectural steels. I think she can explain that better later. So Sarah has held various roles with Tata Steel UK as a research and development researcher in the Swansea Knowledge Group, and later as a technical officer at Tata Steel in Walsall. She also worked in the world of cable manufacturers as a process engineer at Prysmian Group in Wrexham. And more recently, as I said, she's joined Tensor Manufacturing, and I hope that will be her last stop as a product and process engineer. And Sarah's roles have required the use of both technical and soft skills, working hand in hand. Her strong passion for applying academic knowledge to solve manufacturing problems has led her to always work to bridge the gap between universities and industry. So welcome, Sarah, and we're really looking forward to hear what you have to say.
Oh, thank you so much, Julie. Thank you. Can you hear me?
Yep.
Right, let me get my presentation out there. Bear with me. There we are. Nope, there we are. Right, can you see that?
Yes, if you can put it to presentation mode, we will see it better. Thank you.
Okay. That's better?
Perfect.
Good. All right, good evening, everyone. Thanks for holding on until the evening. It's much appreciated. My name is Sarah Lera Mugabo, as Yuli has stated, and today we're talking about my journey as a chemical and materials engineer. My presentation is in four parts. I'll start off by explaining what chemical engineers and materials engineers do and how they are instrumental in tackling some of the world engineering issues currently faced, such as environmental issues and water scarcity. And also talk about my journey as a materials and chemical engineer, but more so being specific on some of the projects I've undertaken. My interest in sharing my knowledge as well through our STEM outreach projects. And later on, just emphasize why it's very important to balance between soft skills and technical skills, and even logical skills as well. And then if you have any questions later on, I shall be very happy to take them on. So what do chemical engineers do? Well, chemical engineers upscale concepts from lab scale to manufacturing place. In small context, scientists are the dreamers, while chemical engineers are the doers. So we get what chemists and materials engineers have come up with, and we try to upscale that onto a bigger place, onto a manufacturing place where we can be able to sell this to the masses. While materials engineering, on the other side, we design and we test materials to be used in products and also processes. So I've been lucky that I've had to tap into material science and engineering, whilst incorporating some of my chemical engineering skills I've acquired over the years in my roles. Chemical engineers and materials engineers are very instrumental in solving some of the issues we're currently facing today, as stated, one of them being solving energy challenges at the moment by being sustainable, where we can get a chance to be sustainable. Materials engineers at the moment are at the forefront of designing and making efficient the solar cells at the moment being used currently on buildings, really. So all that is really what materials engineers do. Of recent, I've heard that at the moment, we're trying to use functional coatings onto the buildings, and the aim is functional coatings can be able to absorb the sunlight. Then the building will store this energy and later on use it to heat homes. Of course, this would be good because then you're offsetting the energy you could have absorbed to use through fossil fuel burning. On the other side, chemical engineers are very instrumental because then it calls up to them to design processes that are more sustainable. One way they could do this is by involving something called pinch technology, which requires them to minimize energy used in processes by e.g. using recovered energy from one process unit and using it to heat another process unit. So energy that could have been lost in one process as waste can be tapped and then used in another to be able to offset the energy we could have acquired in other means. Another way chemical engineers, most for this list slide, can be very instrumental in solving some of the water challenges currently faced in the world today is by using some of the technology. For example, in some places of the world where water is scarce, and if it's then available, it can't literally be consumed in its natural state. So it has to be purified. The way chemical engineers can be very instrumental is they have different technologies such as membrane technologies, reverse osmosis, or even ultra and membrane technologies, which can be very instrumental in purifying this water to make it consumable for parts of the world where the water can be consumed healthily in its natural state. Another technique would be thermal energy, such as desalination. This is very, I think, a better way than membrane technology, and it's still there's competition between, of course, membrane and thermal energies. But a hybrid of the two, I think, would be even a better solution. But these chemical engineering technologies can be implemented to be able to solve some of the water challenges we're using, but mostly in purification stages. In first world countries such as the UK, in processes such as municipal and industrial water and treatment water processes, we have chemical engineering techniques which are employed to be able to purify or treat this water, such as chemical processes, which with a certain dosage of a chemical can be used to be able to create a coagulation and flocculation of materials from the water. Physical processes also, such as screening, sand filtration, and right through to the other one I've forgotten, right through to, I have forgotten the other part. But it's very important to acknowledge that different chemical engineering technologies can be used. In our daily lives, we don't realize it, but they are very instrumental in at least solving some of the water challenges we're facing today. With that introduction at hand, how about me? How do I fit in this big picture? I think for me, before I talk about my journey in chemical engineering, it's important to address where I come from originally. I came from East Africa, and by that I mean I was born in Burundi, raised in Uganda, and then made my way to the UK in 2002. And I was lucky that I had such a strong family who I hold very, very dearly, who supported me and pushed me to achieve as much as I can. I have to point out that none of the people in my family have taken on an engineering course or even a doctorate course. So having them push me to achieve more makes me more appreciative of them. And I have to acknowledge them, hence the slide in this presentation. To cut the long story short, I ended up at Manchester University after my A-levels. I achieved a Bachelor's of Engineering with honours, as Yuli stated, in chemical engineering at Manchester University. I was then lucky to get a scholarship at Swansea University to pursue my master's degree in chemical engineering, and then later on joined an engineering doctorate course in material science and engineering, where I focused more on the flowability of complex fluids through the roller coating process and understanding the material properties and the interaction of operating parameters, how they can influence the quality of the products produced, but also the processability. I was very lucky that during my postdoctorate studies, I worked very closely with industry. For example, during my master's, I worked with a company called Jellygen, who manufacture jellyfish-derived collagen, which is a pharmaceutical grade or medical grade, so to speak, used in scaffolds. So it's important that the purity of these products is on point. So I was very lucky that they gave me a project to start off to be able to design a vacuum dryer, which could then be used to optimize the production of the jellyfish-derived collagen. For my doctorate studies, I worked with Tata Steel Europe within the colors department. And just to point out, the colors department manufacture pre-coated steel that can be used in the production of architectural steels, but also in bakeware and cookware, and then also office furniture. So working very closely with the two companies introduced me to the world of industry. And that's where my passion for me to be able to work in industry immediately when I finished my doctorate was literally inspired. And that's exactly what I did. Immediately after my doctorate, I landed a job as an R&D researcher in Tata Steel. And I again worked collaboratively with Tata Steel manufacturing sites to solve some of the issues they had. Such issues include frictional issues or tribology during cold rollings of steels. Again, rheology during the roller coating process, and all the way to curing issues. But my highlight was exploring alternative cure technologies and determining how good those alternative technologies were with the conventional curing technologies. As I stated before, Tata Steel Colors, the department colors, do manufacture pre-coated steels. By pre-coated, I mean they have a solid steel layer and different layers of coating are applied on the steel and then subsequently heated in the oven, which then of course gives you the curing we're talking about. At the moment, they use conventional curing technologies, but of course to reduce the carbon footprint, they wanted to see if they could explore other cure technologies such as infrared and frequency microwave technologies. And I was very happy that I was part of that project, because then I could determine if, well, through analytical skills, obviously, by the use of thermogravimetric analysis, DSCs, and FTIR machinery, I was able to determine if really the curing we've achieved with these alternative cure technologies can compete with conventional curing technologies. And I was very honored to be part of such a project. I then later on wanted to be much more on site as opposed to being in the lab and on site. So I landed a job as a technical officer at Tata Steel in Warsaw. And my role mainly included improving processes, but also every now and then I would do some analytical work. On the top left, there's the products we made, at least how they should look like. Those are typical pre-coated steels ready to be taken to the customers to deform them in whichever products they want them to be deformed into. On the right is a typical picture of an architectural steel cladding system building. So those are steels which have been pre-coated during roller coating process. And a lot of science goes in there than people would know. And that means understanding the rheology of the coating we apply on it and how it influences the processability, but also the final product. At the bottom, you do have a K bariometer. This is, by the way, in Swansea University, not a Tata Steel, but every now and then when I had a chance, I would work with the university to be able to quantify the properties of this coating. The reason why the K-bar analyzer or capillary rheometry is there is because extensional rheometry is very important in during the separation of material from one roller coater to the other, and then subsequently deposited onto the steel surface. So understanding the resistance of stretching, how that would have an impact on the final quality of the product is very important, because then what you can't make up with the properties, you can make up with the operating parameters. I enjoyed my work there because, as I said, I mainly wanted to improve the roller coating process, but also the curing as well. Now, the bakeware products in this case had a polymer called PTFE, and that's what gave it the non-stick properties. However, to be able to get the PTFE to migrate to the surface of the coating, it was very important that we apply the right temperatures. It so happened that our customers were starting to have issues with why we're not having non-stick properties. So as a technical officer, obviously, what I did was analyze this using a technique called EDS to see if we have the fluorine on top, which we did, but it wasn't there yet. Of course, then the reason why we're having that is because our oven weren't performing. It was then important for us to do some proper background work, which I'm not going to explain because of time period. But we found that we hadn't been scheduling in time to clean the air knives, because over time the solvents would accumulate and block the air knives. And by the time I left, we started to create schedules to be able to clean the air knives, and so as to apply the right temperatures for these coatings to give us the migration of PTFE to surface, and hence obtaining the non-stick properties we want on the steel. I then moved on to investigating and improving process line capabilities at Prysmian. For those who are not aware of what Prysmian is, Prysmian Group is a manufacturing company that manufactures cables. These cables range from low voltage to medium all the way to high voltage cables. I was responsible for the medium and high voltage cables. Now, as you could see on the screen, the cables have a conductor. It could be a solid aluminum conductor, and it could also be a stranded copper conductor. And then you would have an outer screen on it, and then an insulation layer, and then the outer screen. The line I was in charge of would simultaneously deposit these 3 layers onto the conductor, and then subsequently get to harden the 2 layers through the CCV line. I was in charge of making sure we don't get defects during the curing process, and also the extrusion or the co-extrusion process of these layers onto the conductor. I learned a lot because that's where my knowledge of co-extrusion started from, but I had to learn and build more on what I have. I then landed a new job as a process and product engineer at Tensor Manufacturing Limited, where I am at the moment. And Tensor manufactures geogrids. By the way, we have a range of products, just to put that out there. But we manufacture geogrids for application in civil engineering industry. We produce, as I said, different products from Biax products to Triax products. And now we have a new product coming on the market by the names of Interax. And this will be a co-extruded product. But just for today's talk, I would like to just focus on the geogrids, which are Triax. Now, Triax, as you could see, these, of course, you start off by extruding, and then you punch the product, and then you stretch it in both the machine direction and transverse direction. Now, the whole idea is, if for example, the example I'm giving, in road construction, you would have a layer of a geogrid, and then you would apply aggregates. And the whole idea is the aggregates are interlocked within the geogrid system, and that prevents the movement of aggregates from one side to another. And this would provide stabilization of the road structure. And ultimately, this would give you at least try to protect or to avoid any compromise of the road structure over the years because of the interlocking of the aggregates in the geogrid structure. However, we produce products for different applications. This is just one of the examples. Now, where do I come from? Where do I join into this whole process? I am more at the moment involved in the extrusion process. It's a single extrusion process. And then, of course, when the product goes on to other units, we have other process engineers at the moment who are looking at those process units. But with a new product coming on the market, which is the Interax, and it's a 3-layered product, and it's going to use the co-extrusion process, I'll be much more involved in the extrusion process since I have experience in co-extrusion. With regards to equipment specification of this new process for the production of Interax, I've been at the forefront of doing some background calculations and specifying the units we need, and even conducting or developing some of the tests or quality assurance tests, since my background is obviously in research. So understanding the degradation temperatures and what rate of degradation we would need, and also what temperatures each component within the geogrid would decompose out, would able then to come up with a good quality assurance technique to be used for this new 3-layered product. When I am outside of my work, I enjoy sharing knowledge with the youngsters, or at least the next generation of engineers, and making it fun that science doesn't have to be all doom and gloom. It is fun, actually, really. So I've been very involved in science festivals in Swansea University, where I show the youngsters how solar cells work. I've taken part in soapbox science, where I communicate to the audience the wonderful things about rheology and complex fluids and flow, and how we find these in our everyday kitchen, but we don't realize how much science that goes into those products. I've also enjoyed a lot of internal and international conferences where I communicate to industries how my research is able to impact their processes, and also communicate to the academic world my research work, which I was lucky for the international conference. I won an award for the best presentation, and I was very, very thrilled. Right, to summarize all this, I have to point out that balancing is key. I might have all the knowledge, technical knowledge in the world, but understanding that analytical skills have to balance with practical and logical skills. I may not always have the equipment in industry, but using the educational guesses and logic to solve problems is as important as knowing the analytical problem-solving skills. I would like to also give some advice to those who are in industry, who are still students. If you can find ways of getting experience whilst you're a student, that would serve you a lot, because I personally struggled a little transferring straight from academic life all the way to industry, though my research projects were collaborated with industry. But working there as a person is a different ballgame, I can assure you. Communication across departments is very important. So learning to communicate and use your soft skills to create bonds throughout different departments would make your life easier, and that I have to learn the hard way. Understanding that in the industry, you would have a deluge of projects and you have to execute these projects. So learning to prioritize is very important, and knowing to run where for the fire is burning most. This, of course, is when I first started in industry, it overwhelmed me, but then I learned to prioritize. And I would like to think I'm doing a good job. And lastly, time and people management is very important. Learning to respect people's time. That's the only way you're going to have to learn also to get them to respect your time. And knowing when the deadlines are and to make sure you deliver on the deadline is as important. And learning again to manage your manager is very important. Otherwise, you could be overwhelmed. I think one last word I'll leave you with. Don't forget to enjoy the journey. You will find some hiccups along the way, and you will find some joyous moments, but it's all part of the journey. Enjoy. You're going to have to learn to dance in the rain. So thank you so much for listening to me. And if you have any questions, I'll be happy to take them on. Right.
Thank you very much, Sarah. It was quite a good presentation. And Yuli, again, thank you for introducing Sarah as well. I've got one question for you here. One comment to start with, I suppose, they're in awe of anyone brave enough to leave their home to travel to learn in a different country. What made you really choose the UK? And I will add to this, what made you choose chemical engineering in the UK?
Okay, well, I came with my mom. I was 14. So my mom came here as a student, so I had no choice. So I had to follow my mother. And of course, as much as I was excited to prove my mom right, I ended up loving the course. Chemical engineering, I knew my strength wasn't in art subjects, I can tell you that. English wasn't my strongest hold, but I loved mathematics and I loved science. And I love to play around with things to see how they work. I had an opportunity to go to a summer school in Birmingham University. I'm going to try to wrap up quickly. To go to Birmingham University, to this summer school aimed at women to get into engineering. So I had an opportunity to test different engineering subjects, from civil engineering to electrical, all the way to chemical engineering. And of course, chemical engineering appealed to me because there was applied science to it. You didn't have to be overwhelmed with the depth, which at some point you do get there, but you could see where your applied science could really be seen in real world. You could see it. You could see the impact, for example, of rheology, because I like rheology. I'm a rheologist by nature. So that drove me towards chemical engineering and materials engineering, because I could see real life impact. And I love chocolate. So when I went to Birmingham University, they took us to Cadbury, a factory. And well, let's just say they won me there when I saw the chocolate. But yeah, thank you so much. That's how I ended up in chemical engineering and the UK.
Thank you very much. I haven't got any other question from the audience here, but I want to ask you, like, I'm sure you are involved with the chemical engineers, the Institution of Chemical Engineers.
Yeah.
How did you join, or how did you find out about them? Did you find out about them in your studies early on, or did somebody else introduce them to you?
No, when I was a chemical engineering student at Manchester University, they arranged talks during, of course, our chemical engineering courses, and they told us what they do, and also offered us free membership for the duration of our studies. So I reluctantly joined them, and I was more, I think, focused on knowing the graduate schemes as opposed to anything when I joined them. And then, of course, later on, after my studies, I kind of left them behind. And then I realized I wanted to actually get more involved in the, in chemical engineering, Institute of Chemical Engineering, because then it can help me work towards my chartership, which I'm working towards, but also being in touch with the world of other chemical engineers and be able to stay on top of the cutting edge technology and what is happening around the world of chemical engineering in terms of the new products and processes that are at the moment being worked on. So I was in there, got out and came back in.
So would you then say you wish you actually stayed with it and get involved more early on?
No, I won't say so. I think sometimes I have to make mistakes and then learn from them.
Okay.
At the time, I was more involved in my research work. So really, that wasn't part of my agenda until I came back to industry. I realized how vital they are to stay, in touch with your fellow people, so to speak, to know what's happening in the world of chemical engineering, but also be able to work towards a professional qualification as well. So yeah.
Much appreciated.
So thank you.
Thank you very much, Sarah. I think this is all the questions I've got for you for now. And at the panel discussion, hopefully there will be more questions as well. And I will pass it back to Gary or Yuli if you want to say anything else. Thank you very much.